So last time we started K dot P theory, making a break with what we've done so far, although we will be using some of the stuff we've done. Our understanding of the block states at gamma. And so this is what's used by, so this is used by all the optoelectron, especially people who design lasers, and this quantum cascade laser I mentioned. And I guess actually most of you didn't know what maybe I'll just draw a quick picture later. So, all the optoelectronic devices are direct bandgap devices, so this is used primarily for direct bandgap devices. Direct bandgap materials. And the starting point is to just write down Schrodinger's equation. It's very generic. Schrodinger's equation. Here. Where V is just the periodic potential of the entire crystal, and psi would be your wave function for band N and wave vector K. And then you put in this block form where you have the periodic part and the plane wave part. You just substitute that back in to that equation, and you work it through. You take this p squared term, you take this term, and you hit this term with it, and you use, that's a product of two functions of r, u of r and e to the I k dot r. So you hit it twice, like, grad squared. It's confusing. Think of it as d squared dx squared. Just replace r with x. So you hit it twice, and each time you use, what would it be, I guess, like a product rule or whatever. When you do derivatives and you work it through, and you end up with what's written at the bottom of the page, these three terms, each one is multiplied by e to the I k dot r. The right-hand side is still multiplied by e to the I k dot r. So every term is multiplied by this phase factor, which that you then cancel out. And it leaves you with this equation for the u, the periodic part of the block function. And it kind of looks like Schrodinger's equation, except we picked up two new terms, the k dot p term and just the h bar squared k squared over 2m. But that h bar squared k squared over 2m is just a constant. It's a number. It depends on k, but it's not an operator. That k dot p isn't, the p is the operator, right? P becomes the grad, minus I grad. So you picked up a new term, this k dot p term, and that gives you the name of the theory. K dot P theory. And at K, the other thing is that at K equals 0, these two new terms disappear. Right? At K equals 0, your gamma point, which weeks, these two new terms disappear. And so at K equals 0, the solution of these functions U are simply the block states at gamma that we just calculated. In our tight binding model. So at k equals 0, these u's are our usual block states at gamma that we just spent a long time calculating. And then what we started doing was say, okay, now let's think about small k becoming, small, just a small little deviation away from the gamma point, and see how the energy and the these wave functions u, periodic part of the wave functions, change as k starts to become non-zero. And we're going to do that by using perturbation theory. And so we first looked at the energy, first order. So the first order perturbation for the energy is given here using this usual, this is sort of what you learn in Ee208 or in physics for first order perturbation theory, delta E of the energy. So that's all we did here. just taking the first order term, and everything first order in k. So for to first order, you ignore the k squared term, and you just look at the k dot p term. And the only operator is p, so that's the only thing that you need to put inside the matrix element, because k is just a number, depending on whatever k you choose, so that doesn't go inside the integral, right? That bra operator ket is an integral, right? Like d cubed r psi n grad psi n, right? That's what that represents. So yeah, so that's what the first order correction to the energy is, and I guess that's about as far as we got last time. And these n zeros are just our block functions for k equals 0. So, for example, so if this state, n0, has either inversion symmetry or anti-symmetry, then this matrix element is 0. I should just keep the same notation here. This is my n0, n comma 0. So if these states n0 has inversion symmetry or anti-symmetry, then this matrix element n0 b n0 is identically equal to 0. And so for the this is true for silicon and germanium and diamond. Right, because this, these were the block functions we just calculated, so it's going to be a symmetric or anti-symmetric combination of the orbitals on the two atoms of your unit cell. That's what we're talking about. Right, it's what we just spent all that time calculating on. It's going to be a symmetric or anti-symmetric combination of like two px orbitals on the A and the B atom. And since the A and the B atom are identical in silicon, germanium, diamond, these states will have either inversion, and the point of inversion is the point right in between the two atoms. So these crystals in general have inversion symmetry, silicon, germanium, diamond. And the point of inversion is the point right in between the A and the B atom. And if the whole crystal has inversion symmetry, then these wave functions will have inversion symmetry, and this matrix element will be 0. Gallium arsenide does not, because the two atoms are different. So in gallium arsenide, the A and the B atom are different, and so it does not have inversion symmetry. By inversion symmetry, you just replace x by negative x, y by negative y, z by z, negative z, and so basically what that does is just flip the A and the B atom, and since they're different, it's not the same. You don't have inversion symmetry. So this is true for, and it's not true for like the gallium arsenide, etc. But even for the 3,5s is sort of a small change, and this small linear term is generally ignored for these crystals like gallium arsenide, indium arsenide. I mean, you got to be careful. I mean, if you think about what you're doing or will be doing in the homework for graphene, right? The only term of importance is the linear term. This Hamiltonian you're deriving is going to be linear in K. So if you throw out the linear term, you're sort of throwing the whole thing out. So it kind of depends on the crystal, but traditionally in these crystals, which are parabolic, this linear correction is ignored. So that's the first order correction to the energy, basically. Well, for these type of crystals we've been looking at, these diamond-like lattices or zinc blend, your usual semiconductors, you can ignore it. Now let's look at the first order correction to the block function, the U function. All right, so the first order correction to the wave function, if you like. Right? In perturbation theory, you do a correction to the energy, and then you do a correction to the wave function. So for some finite but small k, we can use perturbation theory to look at that. So un of k is un of 0 plus the correction, which we do with this first order perturbation theory. So h bar over m, sum not equal to n, and here's our linear perturbation term, our k dot p term, k dot, which I can pull outside the matrix element because it's just a number, the k part, and then our matrix element, n 0 p n prime 0 all over this energy difference E n 0 minus. So that's the first order correction to the wave function as k becomes finite. At times, I left this out, u n prime of 0. So you're summing over all bands. So n is the band index, you remember. Okay. And at k equals to 0, you've just got your valence bands and your conduction band. And these are usually the only 4 bands that they worry about with k dot p theory. Right? I mean, we saw that there's this band way down there. That's completely ignored. So in k dot p theory, no one worries about that because it's like 20 eV down. Right? And if you look at this denominator as an energy difference, so that if bands that are very far away tend to not be important because of that denominator term. So if you're interested in, say, the conduction band, the sum includes all bands except the conduction band, so you'd be summing over basically the 3 bands of your valence band. And they're going to give you some weight because now these, this is n, but this is n prime, and so one would be like a p state, the other would be a s state, and you're going to get a non-zero matrix element because they have different symmetries. The momentum operator has sort of odd symmetry, a derivative, and one of these wave functions, the conduction band will be antisymmetric, the valence band will be symmetric for something like silicon, and so you'll get non-zero matrix elements. And this whole thing is sort of like, the weight for what you're adding on. So you start off with, just your pure, say, S state at gamma, and then you add on, you start mixing in a little bit of your P states as you move away from gamma, right? The conduction band was pure S state at gamma, and as you start moving away from gamma, you start mixing in some P states. And that just shows up clearly doing this, looking at this perturbation expression. How much you mix in is going to depend on those energy differences in that matrix element. So this is what they call a correction to the central part of the block function. I mean, what we did analytically was just solve the SP3 model right at gamma. But this shows what happens. I mean, it immediately shows you that the states start mixing as soon as you move away from gamma. They're no longer pure S or pure P. So your S-type conduction band is going to have increasing P contribution as K increases away from 0. And in like our last homework, which hasn't been assigned, when you look at the wave functions at x, you'll see that we already did gamma, so the conduction band is purely S-type, valence band purely P-type. But out of x, you're going to see that a couple of the bands are like a 50-50 mix of S and P. So they slowly start mixing as you move away from gamma. Okay, so that's all about the first order correction. So this was all first order in K. Right? We just looked first order correction in K. We considered everything that was first order in K. And now we'll look at second order in K. We'll look at the, not the wave function, we'll look at the energy, right? Because we've already got a linear correction to the wave function. But we don't have any correction so far to the energy, at least for the crystals with inversion symmetry. So, you know, if first order perturbation gives you a 0, then you go to second order, etc., until you get something that's non-zero. So now we'll look at second order, the second order energy correction. And again, it's second order in K. We're looking at what happens as we allow K to move away from 0. Okay, so the second order, what does that look like? Second order correction. Okay, so first we'll just write down sort of something that, you know, you may have seen in quantum mechanics when you did perturbation theory. So E n K, at least to second order in K, is equal to E n for K equals 0 plus, well, you've just got that constant term that now you just add in, h bar squared K squared over 2m. And this is not m star, this is just m, the bare electron mass. Right? There's no m star. In fact, we're going to calculate m star from this in terms of various things. So this is just your bare m over your band, again, n prime not equal to n, of some matrix element squared over an energy difference. And that matrix element squared is K dot n0, n prime 0, closed magnitude squared over the energy difference. And, you know, I don't know whether you've seen something like the second order, sort of second order perturbation theory. But this is just, you know, all this stuff is just that K dot P term over here. This is just coming from your K dot P term. And this is just that constant term showed up in your Hamiltonian. So the K dot P term, we're taking a matrix element squared and cranking that out. Okay, so that's what the expression is. And now, given that, we now have a correction to the energy, and we have something that at least close to the gamma point is, you know, the energy is a function of K. We're now in a position where we can go ahead and calculate the effective mass from K dot P theory. So, and we do it the usual way. 1 over m star in I mean, this is actually a tensor, but I'm going to just try to just look at the diagonal elements. Let me just choose x so it's not so abstract looking. So m star in the x direction. That's going to equal 1 over h bar squared, d squared e. Again, n is the band index, so you'd have a different effective mass for each band. D squared e d k x squared. Right, that would be the effective mass in the x direction. And you can have a different one for y, a different one for z, if your dispersion is different. Curvature is different in x, y, and z. And you can even write down a tensor using a mixed derivative like d squared e dkx dky, and it becomes a tensor. And that's the way I did it in my notes, but that's kind of a mess. So we got to look at this expression that we wrote down and ask ourselves, how are we going to calculate the second derivative of that thing? I mean, the first, this term looks pretty straightforward. That's like what we always do. But that next term kind of looks like a little mess. bit of a mess. It's actually not too bad. Let's see. So what do we got to do? Well, the second, so I mean, let's just do the easy term first. I like doing easy stuff. So if I do 1 over h bar squared d squared e dk x squared of h bar squared k squared over 2m, I'm just going to get 1 over m. Because, you know, k squared is equal to kx squared plus ky squared plus kz squared. So it only hits the kx squared term. So so I pull out a factor of 2, that kills the factor of 2 in the denominator. I'm dividing by h bar squared, so that kills the h bar squared. So that's easy. And this is just, to be clear, this is not an effective mass, this is your bare electron mass. So clearly, to get an effective mass, it's all going to come out of that other term. So let's look at that other term. All right, so we got to take the second derivative of this thing. So, well, I start off, so 1 over h bar squared times the second derivative, which will kill that h bar squared. So I'm going to end up with taking the second derivative of this. Let me write out that dot product. H bar squared over m squared, sum n prime not equal to n. And now my dot product. Sum indices L and Q so I would have KL N0 PL N prime 0 KQ N prime 0 PQ N0 all over the energy difference. That would be my dot product written out in the indices, where L and Q are like X, Y, and Z. So L and Q go from 1 to 3, the indices of X, Y, and Z. And now I got to do my derivative with respect to Kx. So now I have a d squared. Take the derivative with respect to Kx squared. And so I'm going to get 1 over m squared sum n prime not equal to n sum LQ. Okay, so taking the derivative with respect to Kx, I'm going to get a delta L comma X N0 Px N prime 0 KQ N prime 0 PQ N0 plus, there's 2 K's in there, so this is like the first derivative. I still am going to have another derivative sitting out front. Plus the other one, this will be KL N0 PL N prime 0 delta Q comma X N prime 0 PX N0 all over the denominator. These 2 terms all over the denominator. So I'm taking d dkx of this numerator. D dkx of this numerator. And these sums over L and Q are just a sum over X, Y, and Z. I'm summing over the X, Y, and Z components of K. Right? K sub L means Kx or Ky or Kz. So when I do d dkx of K sub L, that's if L equals X, that's 1. If L is Y or Z, that's 0. So that just gives me my Kronecker delta X comma L. And then I have a KL and a KQ, so I have to do this like product rule. There's two independent K's in that sum. And then I do it again, and what I finally end up with, 1 over M plus 1 over M squared, sum over the bands. This index is for X, Y, or Z. And really, we're doing this for band N. So each band would have, this is for band N, so I should really have another index for the band. The effective mass of whatever band you're interested in. So that's, and so we wrote down the second order correction to the energy here at the top of the page, and then I just applied our usual expression that we always use to get the effective mass. And then you just have to work that derivative through, which is what I did kind of in a mess. So you work that derivative through, and you finally end up with this. I mean, the only thing this, the derivative is hitting are the K's. This K, the only thing that derivative is going to act on is this K right here and this K right there. Those are the only things that derivative is hitting. That's the only K in that expression. And so it's just a matter of working through that. And these K's show up in the sum, so those derivatives collapse that sum because they give you these Kronecker deltas. All right, so you work that through, and if you just want, as long as you don't want the tensor, the mix like 1 over M X comma Y, if you just want the diagonal elements of the effective mass, and this is what you get, this expression here for direction I and band N. And well, of course, if you have some degeneracy, you've got a problem with this expression, because then, if these two energies are the same, clearly that's not going to be not going to work. So this is valid for non-degenerate bands, because we just started off with a perturbation theory that was, a non-degenerate perturbation theory. Valid for non-degenerate bands. I guess I have a note here, ignoring spin. When I talk about degeneracy, I'm not including spin degeneracy. All right, so now that we have this expression, now let's look at it and ask, what does it tell us about the semiconductor that we've just been looking at, like silicon or gallium arsenide or something like that. So we can ask, this expression would be perfectly valid to consider the effect of the valence bands on the S-like conduction band. So to do that, we're going to let, in our expression up there at the top, we're going to let N be your conduction band, and N prime is going to be your light hole, your heavy hole, and your split off bands. So now you know explicitly that sum over N prime just means we're summing over the light hole, heavy hole, and split off bands. And N is your conduction band. And so I'm going to use sort of a shorthand notation. I'll call this your conduction band at the gamma point, and I'll just refer to these very generically as your light hole band. Everything is at K equals 0. Your heavy hole band and your split off band. And so we can just put that into our expression up there at the top of the page. And if we do that, we're going to get that 1 over M star of, I guess I chose Z, is equal to 1 over the bare mass plus 2 over M star. And now I'll just explicitly write it. There's going to be 3 terms in the sum, right? I'm summing over N prime not equal to N. I'm summing over those 3 bands. So I'll just explicitly write out each one of those terms. So I've got my conduction band, which I just wrote as C0, matrix element PZ, or the operator PZ, and then your heavy hole band, matrix element squared over the energy difference, which is your band gap, right? The energy difference is the band gap. Plus, again, C0, your conduction band, momentum operator, the light hole band over the energy matrix element squared over the energy difference, which is the band gap, right? Because the light hole and heavy hole are degenerate. They are the valence band edge. And plus, well, the third term, due to the split off band, matrix element squared, C0, PZ, split off over the energy difference, which is EG plus delta. Your spin orbit splitting. So those are the three terms in that sum. And it turns out that the matrix element will explicitly evaluate what these are, but 1 over m star of z is equal to 1 over m, the bare mass, plus 2/3 P0 squared over m squared times 2 over the band gap plus 1 over the band gap plus delta, where this P0 squared, the central parameter of this K dot P theory is, so these are all equal to this PZ squared, these matrix elements. Now, I guess I got to say a little bit about what I mean by these kets here, which I've just kind of, what exactly are these things? Are they the same PX, PY, and PZ that we were doing previously, or are they something else? Well, in fact, they're something else, and I guess I'll talk about them in a page or two. These are the basis states used in the K dot P theory. So they are actually the full block state at gamma of the valence band edge. So if you remember, before we did spin orbit coupling, the block states at the valence band edge were just the linear combination, symmetric combination of PX or PY or PZ. And those were the solutions of the valence band before we did spin orbit coupling. The valence band edge was threefold degenerate, and it was like pure PX, pure PY, or pure PZ. The bonding combination of either PX, PX, PY, PY, or PZ, PZ. And that's what this is the way they write this in K dot P notation. We'll talk about that more in a moment. But now let's just say something about this equation that we've written down here, and that this P0 squared is simply a parameter that we've called for these matrix elements between our the basis states that we use in K dot P theory. So the basis states, this is right the conduction band block function at gamma, and these are the valence band block functions at gamma, and ignoring the spin orbit coupling. And these matrix elements squared of the momentum operator components, PX, PY, PZ, they are all equal, and they're equal to what we call this P0 squared. And these are, in fact, the only matrix elements you get of the momentum matrix operator in this basis. There are no others. So if I try to take a momentum matrix the momentum matrix element between two conduction band, C0, P, C0, I get 0, or between any two p orbitals, I get 0. These are the only ones, and they're all the same. Or between like C0 py and a px state, I get 0. So this is all there is. Okay, given that, well, if we look at this expression here, we're talking about some material that we know something about. So in general, experimentally or whatever, you know ahead of time m star, you know the effective mass of the material, you know the band gap, and of course you know the spin orbit splitting. You know all that from experiment. If these are just all the values at gamma, you know the effective mass of gallium arsenide, for example, you know the spin orbit splitting, you know the band gap, you know everything. What you don't know ahead of time, a priori, is P0. But this gives you P0. So if you know the band gap, you know delta, you know the mass, you know P0. This sort of central parameter to this theory that you need to evaluate the matrix elements, because you got K dot P, so this gives you the momentum matrix element right there in terms of all known quantities. And you need this to do any optical absorption. You always need the matrix elements of the momentum operator. So if you're doing absorption for a laser or LED, you absorb from the valence band to the conduction band. These are the matrix elements you need. And so using this type of formula, you immediately get a good approximation of these matrix elements just in terms of the known quantity of the band gap, the mass, and the spin over coupling. Okay? So that's a very nice thing for K dot P theory. And another thing, just looking at, so given all these quantities, they give you this value for P0. Another thing we can do is just look at this expression here and ask, well, what does it tell us about, say, the relationship between the effective mass and the band gap? Well, maybe it's easy if you just, pretend delta is negligible compared to the band gap, then you can invert both sides. And it's obvious that m star is proportion, kind of scales as the band gap. So m star kind of goes as, I don't know, a proportionality, I guess I should say, not an equality. It's kind of scaling as the band gap. So as the band gap gets bigger, your effective mass gets bigger. Right? That's what that expression tells you, all other things being equal. Right? P0 is just a matrix element of the orbital composition, which shouldn't change too much. But if the band gap, can easily double going from indium arsenide to gallium arsenide, it triples or quadruple, whatever. Then according to this expression, the effective mass should approximately scale in the same way. So we can ask, does it? And, well, yeah, in fact it does. So for direct gap semiconductors, this trend is followed pretty well. This trend is followed pretty well. This is the trend. So down here I'm plotting band gap on the x-axis. Your effective mass as in terms of the bare mass, and what happens to it as the band gap increases. These are all the direct gap semiconductors, and it follows this trend really well over a huge range that we get with this simple, extremely simple version of K dot P theory that we just did. That the effective mass goes as a band gap, and it's, if you just look at that expression, then that is exactly what comes out of this simple expression. you got the effective mass scaling as the band gap. And the one I mentioned, indium arsenide, if I can remember this, like indium arsenide is, let's see if I can remember my numbers. Indium arsenide has an effective mass of, where's gallium arsenide? Gallium arsenide, oh, here's my gallium arsenide. So the conduction band mass of that is, that one I remember, 0.067 M0. And indium arsenide is, well, if that my scale right, yeah, this is what I remember. Like, I think it's like 0.03 or something on the order of 0.03 M0. Indium antimonide is ridiculously low. This is like 0.015, I think, M0. Anyhow, so as you can see, what we derive with our simple K.P expression does indeed work really well for the direct gap semiconductors. Now we're going to talk about those basis states, these XYZ basis states that we use, and actually explicitly calculate, do some somewhat explicit calculations of this matrix element P0. And it's like, again, one of those things where you do a lot of calculation and you pick up this factor that I sort of threw in without really mentioning where it came from. This factor of this factor out here, like, where did this factor of 3 come from? I really didn't say anything about it. It's like you got to do a lot of work to actually find out where that factor of 3 comes from in the denominator. So, first of all, let's be clear about what these XYZ states are. This is really the basis we're working in. And this is the way people just write it down who do K.P theory, which I've always found just a little unsettling. Because if you come from a localized orbital perspective, you want to know exactly what do they mean by X, Y, and Z? What is that state? Because you're thinking in terms of some, orbitals on silicon atoms. So to be specific, going back and forth between the two, this K.P and what we just finished, which people call localized orbital theory. So the S in K.P is...
I think it's frozen.
Yeah, it should. It doesn't like these pictures or something. You can do it. There we go. So this S in our K.P is going to be, well, again, they write it, usually the theory is written without the spin-orbit coupling, and that's included explicitly in the Hamiltonian, as we'll see later. So you'd have this for both up and down spin, and then just duplicate it. So this, okay. So this is equal to 1 over root 2 times what we would usually write down for our conduction band edge at gamma. So S on the A atom minus S on the B atom. So that's just our block state, right, for the conduction band edge. That's all it was. That's what we calculated before. And these guys, the X, Y, and Z, there are bonding p orbitals. And for example, this guy would be 1 over root 2 Z on the A atom up minus Z on the B atom up. So this was our bonding, right, our bonding p orbital for the valence band. And you'd have the same for X and Y. That define the valence band edge in the absence of spin-orbit coupling. Okay, and so as we said, the only non-zero matrix elements of this momentum operator are S, PXX, S, PYY, S, PZ, Z. Sometimes people define this with an I in front of it. As far as I can tell, this doesn't make a lot of difference. The important point is that they're all equal, and these are the only ones that there are. And so what we have to do now is do a lot of work to get that factor 1/3, basically. So we will explicitly calculate these matrix elements in terms of the P0 and the band edge states. So to do that, let's look at so we're going to specifically look at some matrix elements between the band edge states and the conduction, like heavy hole to conduction, light hole to conduction, etc. We'll start off with heavy hole since that's the simplest one. All right, so the heavy holes were these 3 halves, which is -1/√2. And now I'm going to start mixing this K dot P notation with what we did before. So X up plus I Y up. And these, when I write this guy and this guy are our K dot P basis states, which means they're what I wrote down here. So these, when I write Z up, what I mean is this. Right? When I write X up, what I mean is, XA up minus XB up. So it's just a shorthand way to write this. So this is what going back and forth between what we just derived and using this K dot P notation. So this is what our 3/2 state was, and the only other one I needed is the 3/2 negative 3/2 for the heavy hole. So 3/2 minus 3/2 was equal to 1/√2 x down minus IY down. And our conduction band, which will stay the same for all of this. And these, again, I'm using the K dot P notation where that's just the antisymmetric combination of SA and SB, right? That's all that is. And so now we can look at the matrix elements. So we've written our band edge states in terms of our K dot P notation. So S up P 3/2 3/2 is equal to S up, and then you got to write P as a vector, so you got to write it out. X PX X hat PX plus Y hat PY plus Z hat PZ, acting on our 3/2 3/2 state, which is X up plus I Y up, all times 1/, I guess, negative 1/√2, I guess. Negative 1/√2. And so now we just evaluate the non-zero matrix element. So that's equal to negative P0 over √2. Well, if I look at over on the right-hand side, I'm only going to get a non-zero matrix element between this and that. And for Y, I'll only get a non-zero matrix element coming from this term, right? Because those are the only non-zero ones we get. So I get, there should be a P0 times X hat plus I Y hat. That's what you get. That's the matrix element, right? I started off taking a matrix element of a vector, so the final answer has got to be a vector. It's a funny vector because there's one of the components is imaginary. But all right, I'm taking the matrix element of a vector, and so the final thing is going to be a vector. And then we're going to see this when we do like optical absorption. This is really important because we're going to look at like circularly polarized light, where you got to take the dot product of E dot P, and E you write as like a phasor, so E is complex, and you're taking dot products, so all these imaginary terms become kind of critical in getting the final answer. Okay, so the other one, we got 1 minute. Let me do the other one. So we're done the heavy holes. So S down, P, 3/2, negative 3/2, is equal to, well, you got to write it all out. And so that's equal to y hat. You all see that? You agree? Okay, so we've got those are the only two matrix elements you get between the conduction band states and the valence and the heavy hole, because if you notice, the heavy hole state is actually a pure spin state, right? This is down and this is down, so this is down. So I won't get any matrix elements with S up. And if you look at the other 3/2, 3/2 states, that's also a pure spin state. Where did it go? So I mean, this is up, this is up. So both of these states are pure spin states. So I'm only going to get a matrix element with this guy with S up, because right, momentum doesn't couple spins. Momentum doesn't. So they have to. I'm only going to get non-zero matrix element with terms of the same spin. So I get S up with the 3/2, 3/2 state, and S down with the 3/2, negative 3/2 state. And then we'll do light hole and split off next time.